Hello, everyone. Thank you for attending today's webinar. My name is Ahmed Abu Mazwood. I'm staff scientist photonics at CMC Microsystems. So the webinar is about OptiSPICE standalone electro-optic circuit simulation software by OptiWave. And our speakers are Chem Bonfil, who is the product manager of OptiSPICE at OptiWave. Saurabh Bedi, he's an application engineer at OptiSPICE team, OptiWave. So I will start the webinar by giving a brief introduction to CMC Microsystems, and then Chem will give introduction and background of OptiSPICE software. Saurabh will also give detailed demonstration of the OptiSPICE simulation tool. Questions and answers will be at the end, so you can use chat window to post your questions, or you can use the raise hand Zoom feature before you unmute yourself. So until then, please keep your microphones muted. So CMC Microsystems is a not-for-profit organization founded in 1984. We manage Canada's national design network, and we provide infrastructure for innovation. We provide services to simplify access and reduce cost to advanced technologies, including microelectronics, photonics, MEMS, AI, machine learning, and also quantum technologies. We offer services under 3 categories: CAD, Fab, and Lab. So under CAD, we provide computer-aided design tools and design environments. We have also a secure distributed private cloud for hosting. We also provide user guides for the tools themselves or for process design kits by foundries. We have application notes, training materials, courses, and all that is backed by engineering support. Under Fab, we have multi-project wafer services through many foundries. We have microelectronics down to 12 nanometer. We have silicon photonics, MEMS, nanofabrication. And under Fab also we have packaging and assembly services. Under Lab, we have platform technologies to speed up your research. We have also the test equipment loans program for short-term needs. And we also have international partnerships for any unique needs. As I mentioned, for multi-project wafer runs, we have low volume prototyping for academia, and also we have dedicated runs for high volume, for example, for startups, and all and the access is through foundries and partner organizations, including many applications in microelectronics, photonics, opto-electronics, MEMS, microfluidics, advanced packaging and assembly services. And all that is backed by engineering support and consultation by CMC Microsystems. So for industry, we have the Virtual Incubator Environment Program, which is mainly for startups. So we allow access to CAD, Fab, and Lab under this program. So please contact me if you need any information. And that's it from my side. I'll over to you, Jim.
As Ahmed said, I am the product manager of OptiSPICE at OptiWave, and I will give you a brief introduction to the software and talk about the background before handing it off to Saurabh, who's going to go deeper and show you how the software works. This is a 2-part series, the first presentation of a 2-part series presentation, and we're going to be focusing on OptiSPICE standalone. And our next presentation is going to be about the plugin version. So what OptiSPICE does is it is an electro-optic circuit simulation tool. It takes its roots from the standard SPICE, which was initially developed as an analog circuit simulation tool, and it is commonly used for electrical IC simulations. So what we did, we extended a standard SPICE to allow optical simulations, so we can simulate optical and electrical devices within the same simulation engine and the same working environment. So it's our optical and electrical devices are fully integrated into one engine, and it gives us a certain series of advantages. For example, it is very good at handling electro-optic feedback loops, and our simulator also can handle multi-mode, multi-channel operation for optical devices. We can do time domain and frequency domain analysis, and we can handle linear or non-linear electrical and optical devices. So this is pretty much it for this slide. So like I said, due to its system matrix approach, where we put all the equations on electrical and optical in one single matrix, we can handle the feedback loops, we can do link simulations, multi-domain, and in some instances, we can also do thermal and optical and electrical at the same time. And we're also focusing on enabling users to do photonic integrated circuit simulations. So you can do photonic integrated simulations with standalone SPICE, and our plugin version is more specialized towards enabling electro-optic integrated circuits. So next time we're going to talk about that. And now I will hand it off to Sarab to show you how our software works. And he's going to be initially talking about some electronics before moving on to optics.
Thank you so much, Shem. Hello, everyone. I'm Saurabh Bedi. I'm the application engineer in OptiSPICE team at OptiWave. So I'm just going to share my screen. All right. So as Chem briefed you about the software, so it's an electro-optic circuit simulator based on SPICE engine, and it's very much capable of handling electrical and optical simulations in the same domain. So in my part of the presentation, I'll be going through the functioning of the circuit, and I'll be showing you how we can set up different simulations like the AC, DC, and the time domain simulations, as well as the frequency domain simulations. And also, I'll be going through some complex circuits, and I'll be telling you how you can create sub-circuits out of your complex circuits and create your own library and save your circuits like that. So I'll be going deeper into this software. So this is how the OptiSPICE standalone simulation software looks like. So once you open a new schematic, this is how it will look. It's the Schematic Editor. And on the right-hand side, you will see all the elements which are in the library. So there are different libraries. If you look at the drop-down menu here, so we have Electrical Library, wherein you will have all the electrical elements, all the basic and some complex electrical elements. Then if you go to the Optical Library, here you will see all the optical elements like circulators, isolators, beam splitters. We have couplers and single mode and multi-mode fibers and waveguides, etc. And also we have the S parameter elements, which allows user to load the optical S parameters. And then moving further, if you look at further, we have Opto-Electronic Circuits as well, like the lasers. We have different types of lasers: continuous wave, voltage control lasers, thermal lasers, etc. Modulators and all. And then we have some thermal devices. We have different kind of probes and visualizers and everything. So that's the list of libraries we have. And now I'll be showing you like how we can set up the DC analysis. So for that, I'll be just basically building a small circuit, and I'll be showing you how we can set up the simulations and how to extract the results out of it. So unlike other simulation software, like for this one also, you can just simply drag and drop the devices. Let's say you have any any number of elements to make your circuit, and then you choose the wire and make the connections out of it. And so yeah, simply you just need to drag and drop and place your circuits here, and that will allow you to build your circuit. So this is just an example. Now quickly I'll move to the DC analysis. So that's an example of DC analysis wherein we have a diode, and which is connected to the DC source, and there's a resistance which is further connected to the ground. So in this particular simulation, what we are trying to get is we will sweep the DC source and we will extract the diode current out of it. So so we have connected the diode, resistor, and DC source and the at the ground. And we have like from the probe, if I, on the right hand side, if I just type probe, it will pop up 3 different types of probes. So I have connected the probe visualizer here to the pin of the diode. So you have to make sure that when you are measuring the current, you need to connect the probe to the pin of your element. And in this particular simulation, if I double click, this will open the diode, and here you can see the list of different parameters of the diode. For this particular example, I have just enabled the area, and I have in the values section here, I have given a parameter named area. Now, in order to set up the simulation, you here in the toolbar, you will go to the analysis, then you will go to the setup. This is the main setup simulation window, wherein you in front of the simulation type, if you see, if there's a drop-down menu, you can see transient AC, DC, and operating point analysis. So you can choose whichever simulation you're running. Then we have the enable sweep. This is checked because we are going to run a parametric sweep here. Then we have the SPICE command. In this, if you click on this box here, it opens up a window wherein you can define all the parameters, or let's say some set of equations if you have, in order to build your circuit. So everything can be defined over here. I'll be coming to that later. Then also there's an option of running the post-processing of your circuit results in Python. So if user wants to just analyze its results later on and do some post-processing, they can write a script in Python and then just define the path over here. Just click over here, and then we can define the path here, and that way we can give the we can set up the path, and then we can run after running the simulation in your script. So yeah, so here we have the diode, and sorry, I think yeah. So here, like I said, we'll be sweeping the parameter area. Now to set up the parameter, we'll go to the parameters tab here. Here you can see, like, we have already set up a parameter named area, and if you click here, it will show you 4 different values. So we'll be sweeping area from 1 to 4 meters square, and I will show you how to set up a parameter. So we hit add. We go to the category parameters. Let's say we want to set up the parameter T1. And then again, we name it T1. In the type, we'll go to sweep. Then in the value, just hit 1 and add. This will add your parameter here. Then you go to this box, and you can see here it's nested level 1. So this shows that it allows user to set up the nested sweeps as well. So if you go to total sweeps, here you can see set the nested level. So right now we only need 1 set of sweeps. And then here we can increase like whatever number of iterations you want. You set that, and then you select all of them, and you can spread the iterations linearly, exponentially, or logarithmically. So in this case, let's say I choose linear. It starts at 1 and ends at 4. Hit OK, and here you will have one linearly. You'll have your values linearly arranged, and then just hit OK. So that's how you set up your parameters. But for now, like I said, we have already set up the parameter area. So I'll just remove this one. And now we'll go to the DC tab. Here we will set up the simulation settings. So our source name is VDC1 here. So we will write VDC1 here. Then we set up the start value from 0.1 volt to stop value 0.6 volt at an increment value of 5 millivolts. So once you have set up your DC your DC simulation settings, you go to main. Just make sure that you enable sweep here, because this will allow to go this will allow the simulation to go through the different iterations which we have defined here in the parameters. So once you have enabled it, hit OK, and then when you hit analysis and run, yeah, here you see it has gone through 4 different iterations. And now, once the simulation is completed, you hit the launch waveform viewer, and then you go to the DC graphs. Here you will see the set of different iterations and their corresponding graphs, whatever you are extracting out of it. So in this case, we have the current of the diode as a function of voltage. So this is iteration 1. We can just drag and drop on this one, and this will show you your the result of your of changing the parameter area. So that's your diode current as a function of voltage for different areas. So this is a basic example of the DC analysis. Now, moving further, I'll be showing you how we can also set up the AC analysis. So this is a circuit for a commercial op-amp. Like I've modeled it internally, and so basically we have AC voltage source here, and the signal from here, it goes through the first stage, wherein we have certain set of resistors and capacitors, and then this allows us to set up the input offset voltage for the op-amp. And then we can set up the input bias current. We can set up the input offset current, and then this capacitance and resistors allows us to set the differential or common mode capacitance or resistance for an op-amp. Then this second stage is basically it's a voltage controlled current source, which is connected to resistor and the capacitor in parallel, which allows us to set the cutoff frequency of the op-amp, and then followed by it is a unity gain, and then we have further we have diodes, and then we have the voltage power supply here. And to read the results out of it, so basically this should give us the gain in voltage as a function of frequency. So to extract the results, we have connected the probe visualizer here just before the resistor in order to measure the voltage. And once you have built your circuit, you just go to again the main setup window here. In the simulation type, we'll set up the AC simulation, and in the SPICE command here, like what I was telling you before, here you can see the list of all the parameters which I've defined, and also there are like certain set of equations here. So whatever equations you have or the list of parameters, you can always set them here in the SPICE command window. So here I have the list of all the parameters values, and some of them are a set of equations. Then once your simulation is set up here, then you go to AC tab, and here in the AC sweep type, there are options for linear or decreasing frequency. I've set up the decreasing, so I've set the number of frequency points to 1,000, starting from 1 kilohertz to 100 megahertz. Then once your whole simulation setup is complete, you set your simulation setting, then go to analysis and hit run. So you can see like your simulation has been completed. Now either we can go to launch Waveform Viewer, and view the results, or also we can just double click on this Pro Visualizer, and that will give you your your response. So here you have the V out magnitude, which is basically the gain as a function of frequency. And also we have the phase of your op-amp as a function of frequency. So a user can always extract the result by going here and export data, and just hit the export display, and then you can save your data in the text format, and then you can use it for the analysis. So so this is an example for how you can set up an AC circuit, any circuit, and run an AC simulation from it. Sorry. Then now moving further, okay, before I move further, like I would like to show you that whatever complex circuit you build, you can always extract a netlist out of it. So in order to have a netlist, you go to analysis and then you hit view netlist. So this is the SPICE engine netlist for your circuit, which will list firstly, if you have any parameters, it will list all the parameters. And then it will tell you what are the simulation settings and everything. And then it will list all your devices here. You can see all your devices, and they all are connected basically with each other. So this gives you the netlist. You can always double check, and you can always run your simulation from here as well. If you go to run, you go run netlist, you see it runs again from here as well. So that's how you can extract the netlist of your circuit, just to be double sure like your connections are proper or no. So that's for the AC sweep. Now I'll quickly tell you how you can create a sub-circuit out of your any complex circuit. So sometimes if you are working with very complex circuits which has hundreds or thousands of elements, so it's always good to create your own small sub-circuit and use it as a whole instead of using complex circuits all the time. So like I said, this is an op-amp. So I'll be creating a sub-circuit wherein it will contain all the parameters, and it should function similar to this circuit. So in order to create a sub-circuit, what you do is, like, once you are confident that your circuit is working fine, then after that you go to options, go to the sub-circuit, and then hit new port connector. Here you will have signal port connectors. It's set to input. You can change it input or output or bidirectional. For this one, it's set to input, and let's say I have to set up a port name. Let's say I set it up in plus, and then you hit place, and then you can put it anywhere on the schematic. And for this particular op-amp, I'll be needing in total 5 ports. So what I can do is just I can make the replicas and the copies of all of these ports, and then I can click on each of them, go to right click, go to edit, and then I can just change the names of each of the ports. So that is input plus, input minus. This one is out, Then we have V plus, and this one is the V minus for the voltage supply. So this is V minus, right? And then we have to connect these ports to your wherever you need your inputs or outputs. Then you need to connect these ports. So once you connect them, it should look like this. So this is basically the same circuit of the op-amp. What I've done is I've just connected these ports here. I've removed the voltage source from here and basically connected the input port here. So this input port will allow you to send the voltage in. And at the same goes at the output. Like here, I have put the output port. I've removed the load resistance from here, and in here I've connected these DC sources, and I've replaced it with the voltage supply ports. So this is how it should look. So we have input plus, input minus, V plus, V minus, and V out. So that's how you connect your ports. So whatever inputs or outputs you have, you can just create ports and connect them. Now, once you have connected your ports properly, then again you go to options, go to sub-circuit. Now go to create sub-circuit block here, and it will give you different options. So you can select a circuit file that is already open in a, hit next. Yeah, okay. And then it will show us the list of all the circuits which are already open here. So out of which I will select this particular circuit wherein I have connected the ports, then select, and then you see automatically it has detected all the ports and it has detected the positions as well. So on the left pins, it is input plus, input minus, output pins, right pins, it's output, top is V plus, and bottom is V minus. So it has automatically detected the ports. And then make sure you select the place by position in sub-circuit in the default pin placement. Then hit next. Now, let's say now we have to name it. So let's say we name it as op-amp 1. Okay, now you can select the name display setting. So I've selected display the name using the part attribute field. Then hit next. And now it is asking you to save it in a certain set of, in any specific library. So here user can always create their own library. Like you can go to new lib here, select this one. And in here, like go to library section, and you can give any name to your library, let's say, and then hit save, and that will create a new library, and then you can save that your circuit in that particular library. But for now, I have already created like this my spice lib. It's a library which I have created for myself. So a user can create their own library and then just save it in here, hit finish. Now if I on the right hand side, if I go to my spice lib, which is my library, you see here we have the op-amp. So now you right click on it and go to edit part. So that's how your sub-circuit looks like. So we have you can see all the pins here, 5 pins. Now one thing I would like to mention over here is that all these pins are electrical by default. If let's say you are creating any optical sub-circuit, then you need to, here they are listed, here all your ports are listed. So you right click, go to attributes, and then in the type here you need to type optical here if you want to make your pins optical. But in like this is an op-amp and we don't need an optical one, so we'll just leave it like that. And this thing, like if you need to change all your pins to optical, you have to right click on each one of them, go to attributes, and then in the type you have to write the optical. So in order to convert them. Now, this is your sub-circuit. Now, let's say if you want to, generally op-amps are shaped like in the triangle. So you can always create the circuit in your circuit, something like this, and then you can place your pins from here, right? And that way you can create your sub-circuit like that, and delete the older one. And you can delete the older one. Yeah. So trying to place it. Well, we can arrange it like I can just drag the triangle and I can place it in proper, but you get the idea. Like that's how that's your op-amp, and it has been modeled. Then once you have completed your sub-circuit design, you hit close, and then it will ask you to save changes. Make sure to say yes, and then you will have your op-amp here in the library, you can see, which you have just created. And then like this one I created from here, but there's already an op-amp which has been created before, and you can always test it. So you can just create any circuit. Then let's say this is already created for an op-amp. So let's say this is the op-amp sub-circuit which we have just created. You can just drag and drop here, make the connections. And once it's connected, like you can just go to the simulation again, settings again. In this case, again, it's AC, and I've set up the simulation settings. You go to analysis and hit run, and that should give you your result similar to what you have modeled before. So here again you have your gain as a function of frequency, and then you have your phase as a function of frequency. So that is so this allows you to just create a sub-circuit out of any complex circuit, and you can always save it in your library. You can save it in any existing library, or you can create your own library as well. So yeah, so after this, I'll be moving to the next demonstration, which is for the frequency domain simulation, like how we can set up the frequency sweep or wavelength sweep. For this one, now I'll be moving to the electro-optic circuit. So here we have some optical elements as well. This is basically a 2x2 flat top filter. And in order to build it, I've used the cross couplers, which is from our optical library here. If you go to optical, you have a list of all the optical devices. So if I just type coupler, I get the cross coupler, right? So you can just drag and drop and make the connections. If I double click it here, you can set the coupling coefficient values. So I'm using here the cross couplers. So I'm using 3 different cross couplers with 3 different ratios. For the first one, it's 0.5. For the second one, it's 0.28. And for the third one, it's 0.08. And then this is the first stage MZI. So these cross couplers are connected using a waveguide. For the waveguide here, we are using the multi-layer filter explicit, which is this one. So this is basically a filter which has n number of layers. And if I just double click it in the main window, you can see a list of connected voltage pairs to layers. So here we can have a matrix or list of different voltages, and these voltages can be used to tweak the ineffective or of any layer, of any particular layers. And here again we can define the matrix of initial values of connected voltages. If we click on this button next to the model, here you will see the model definition of this multilayer filter. So you see the model multilayer filter, and filter type is explicit. Here it shows N naught, NF, index, and the thickness. So the N naught is basically the refractive index. The effective refractive index of the first layer. Then we have the NF, which is the effective refractive index of the last layer. And in the index here, you can see the matrix. Here we can define number of refractive index values for different layers. And the thickness defines basically the length of the whole device here. So, but since we are modeling it as a single waveguide, so the N effective is basically the same for the first, last, and all the layers. So basically, the N naught, NF, everything is equivalent to N, and this N is basically the N effective, which I have defined in the SPICE command parameter section, and L1 is the thickness of the waveguide. So that's how you can set up your waveguide as well. So as you can see, I've set up 4 different waveguides, and they have the same refractive index, but their length is different. So and also another thing, if you notice here, is like all your optical elements are connected via pins in green. So you can see the different color coding. They are electrical circuits here. They are in blue. So this distinguishes your electrical as well as your optical circuits. Then so like I said, I've defined the parameters here. Now, if I double click on the setup window, if you go to the main, here in the SPICE command, I have set up the list of parameters. So I've defined the N effective, I have defined the length, L2, delta L, L1, all the lengths of the waveguides again, and then I'll come to the settings later. Then now here we are sending the signal in from a laser, which is a voltage controlled laser, and we have a DC in order to control this laser. This will send in the frequencies, and in this filter we have a photodiode, and we have which is connected to the DC source to operate it, and there's a resistance to read the voltage signal out of it. And we have connected the probes here on both the arms. So to read the transmission, we are using the photodiodes here. Now, how we set up the frequency response. So basically, in OptiSPICE standalone, we have an interesting way to run the frequency sweep. So we have here you can see another DC source, and you can see a wire coming out of here, and we have named this. I've named this wire as VLAM. So basically, VLAM is basically the node which is coming out of the DC source, and this node is virtually connected to this laser over here. So if I double click, if I open this laser, you can see like here we have an option of setting the frequency shift, frequency units, everything. But if you go to the optional tab here we have the carrier frequency node. And I've set up the value as VLAM, which is similar to this node. So basically what we are doing here is we are virtually linking this node with the laser over here. And what we are going to do is we are going to actually run a DC sweep, wherein we will sweep this VDC4 source, and this VDC4, like these DC values will actually give us the values of the frequencies, like they will generate the correct frequencies. So how? So let's say we open up the simulation settings, we select the simulation type as DC, and then we go to the DC tab, and in the source name here, we'll select the VDC4, and then let's say I'm interested in the wavelength range from 1545 to 1555 nanometers. I set up that, then I set the increment value. So basically we are sweeping the VDC4 here, and since it has a node VLAM which will drive this laser source here, and and in the output, like once the simulation is completed, in the transmission, you will actually see in the x-axis, you will see the DC, like the VDC values. So let's say your simulation is set up now. We have set up the node. We have set up the node in the laser. Then you go to analysis and hit run. Okay, so it's completed. So now if I open this probe, if I double click this probe, yeah, okay. So if I see, you will see the response of the filter, like it's a flat top response. And here in the x-axis, if you see, we have DC values ranging from 1545 to 1555. So basically, it's mimicking the wavelength, but actually, in reality, you are sweeping the DC source. So that's how you can run the frequency sweep for your circuit, and in the same way, let's say if I go to analysis, if I go to launch waveform viewer, so we have the DC graphs here. So that's the signal one, okay, and then we have the other signal. We can just drag and drop on this one. So here you can see the response coming out of two outputs, and you can see the flat top filter response here. So so that's how you basically set up the frequency sweep, or I mean the wavelength sweep, and you can use the DC simulation settings. Okay, now after this I'll be moving to the transient analysis, but for the transient analysis, like I'll be showing you the same circuit but with the time domain simulations. So let's say if I open this circuit, I'll be selecting two different wavelengths, where we have the flat top. So that's the resonant peak here. So it is at 1549.22 nanometers, and for the other channel, it's, let's say I pick 1550.04. Now, for the transient, it's basically the same circuit now. It's the same 2x2 flat top filter. For the output, we are using photodiodes to measure the response. But here we have two different two laser sources, each set up at the wavelength of interest. So here we have set the frequency to 1549.22, which I just showed, and I've changed the frequency unit to nanometers. And in the same way, the other sources here is 1550.04, and I've set the frequency unit to nanometers. And to drive these laser sources, I've used the bit generator here. I've set up like the line code NRZ. I've set the rectangle shape to exponential. Then I've set the amplitude, bias, bit length, rise time, fall time, everything. And then if you go to optional, here we have the bit stream, and I've randomly set it to like 0, 1, 0, 1, 0, 1. And the same thing goes for the other bit generator, but in here we have different bit pattern. So what's going to happen is like once we'll run the simulation, we'll see this channel coming out here at output 2, and channel 2 here will be coming out at output 1. Then once you have set up your circuit, you go to the simulation window, simulation type as transient, and then go to transient, and then you can set up your time settings here. I've set the step size to 1 picosecond and stop time to 6 nanoseconds. Hit OK. Go to analysis again. Hit run. Okay, so we can close this. Now, if I double click this, so you see here we have 1, 1, 1, 0, 0, 1, which is the second bit stream pattern. And if I go to this probe, we have 0, 1, 0, 1, 0, 1. So like I said, the channel 1 has been obtained at output 2, and channel 2 has been obtained at output 1 over here. So that's how you can set up your transient simulations. And if you look at these response, so you will observe some wiggles. Some wiggles have been observed, which is basically the interference, and there's some like ringing effect due to the channel crosstalk. So because that's how like you can set up the transients simulations for your circuit. Now, moving further, I'll show you how we can how you can set up the circuit. Like let's say if you have a complex opto-electronic circuit and you have run 3D or 3D simulations for any of your optical devices, and you have the S parameters and you want to use those S parameters in order to have a chip layout or like chip level circuit simulation, you can do that as well. So if you see here in the optical library here, we have the optical S parameter 2-port, we have 3-port coupler or splitter, and also we have S parameter 4-port as well. So for this one, I have set up, for this example, I've set up a basic ring resonator, so which comprises of 2 S parameter port over here, and there are 2 waveguides. Again, you just have to drag and drop, make your connections, everything, and here we'll be sending the signal from the laser source over here, which is driven through DC source, and again we have set up the node VLAM, which will drive the laser source over here virtually. So, and then the signal will go through the first S parameter 4-port to the first port, and then you will see the throughput response, and a part of the light will travel through the ring and you will see extract the dropout response over here. So it's a basic example for ring resonator. If I just double click this S parameter port here, you will see the input file name. So basically you have to define the file name of your S parameter, which is in the text format. And the SPICE engine, normally it takes the Touchstone format. So you have to make sure that your S parameters are in the Touchstone format. And also make sure that you have saved your S parameter text file in this in the same path as your circuit, where your circuit simulation file is saved. So your text file needs to be in the same directory as your circuit simulation file. And that's it. You just have to name your S parameter text file. So in this case, it is a MMI. It's a 5050 MMI S parameters. So I selected that, and same goes for the other S parameter port. And to make the waveguides, I have again used the multi-layer explicit model, and in here I have defined the N effective here, and I've defined the thicknesses. And these parameters are again defined here in the SPICE command engine. If I go to SPICE command, here you will see the N effective and the lengths of two waveguides. So this forms the ring resonator here, and then again we are going to run a DC sweep in order to run a frequency sweep. So I'll select the DC here in the simulation type, then go to DC, and here in the source name I'll set the VDC2, and the wavelength range is from 1548 nanometers to 1552 at a step of 0.001. So once this is set up, again, I'm using the probe here to measure the transmission response. Then go to analysis, hit run. Okay, 1 second. So once it's done, double click, and here you can see the response coming out of the throughput of the ring resonator, and at the x-axis you will see the wavelength range, or in this particular case the DC sweep range, and on the y-axis we have the transmission. And same goes for the drop port here. So that's your drop port. Like I said earlier, you can always go to the launch waveform viewer, and you can just drag and drop your signal here to look at your drop and through response. So that's how your response looks like, and you can always export data in text format by going here, export data, and export display here, and then you give the path, and you can save your results in the text format. So yeah, so that's for the that's about how to use the S parameter ports. As you can see here in the list, we have 3-port as well. Like for example, you have a 1x2 MMI, or you have some couplers. You can use that too, as well as you have one 2-port S parameter element as well. So yeah, using these devices, you can load data for your FTDD simulation results, and you can build your circuit for, let's say, any chip level circuit design. So this allows you to build your circuit using S parameters. Now, also we have hooked up the OptiSPICE standalone software with the MATLAB as well. So what happens is, like, instead of using these normal probes, we can use the probe MATLAB, which will open your results in MATLAB. And also there is a way to run any MATLAB script. Like, let's say if user has to do some post-processing of its simulation results in MATLAB, there's a way to define a path. So there's a code in JavaScript wherein you define the path, and then once you double click on the probe, it will automatically show you the results in MATLAB, as well as it will run your script for any post-processing analysis. So let's say right now I'll just be showing you how, which is the MATLAB probe here. And then eventually you can use that to view your results in MATLAB as well. So here is the probe MATLAB. Just connect it to the wire over here. Okay, and then let's run it one more time. Okay, now if I double click it, it should pop up the MATLAB window and show the results. Yeah, it takes a little bit of time, but yeah. So you see here, it shows you your results in MATLAB. And like I said, there is also a way to set up your MATLAB code or any script for doing the post processing as well. So and then what you have to do is to define that the path for that particular MATLAB code in the Java script. And once you will double click your probe here, it will open the MATLAB, it will open the results in the MATLAB, as well as it will run your script, and it will give you the results of your post processing as well. So that way, so this is just a demonstration to show that we have kind of hooked up the OptiSPICE engine to MATLAB as well. So, and also, like I said, we have there are certain examples in the already built in for the Python post processing as well. So wherein you can see that there's a Python file which has been specified over here, and then once you get your results, then like in the launch waveform viewer, you just have to, sorry, once your simulation results are done, it gives you an option to view your results in Python, and you just hit the launch Python button over here, and that will pop up that will run that script and give you the results out of it. So yeah, so this launch Python. So user can always set up like you can always do the post processing of your simulations in MATLAB or in Python. So that flexibility is also there with the SPICE engine. And I think yeah, that's pretty much. And now I would like to yeah, so that pretty much sums up this tutorial for this OptiSPICE standalone software. Now, if you guys have any questions, we would like to take on the questions now. Thank you so much.
Yeah, we can take the questions live. I don't think anybody has the right to post questions right now. So if anybody wants to ask a question, I think you can use Zoom's raise hand feature. So we'll try to keep things in order. We can also talk a little bit about, if nobody has questions, we can talk a little bit about the plugin and maybe show you some more advanced examples of OptiSPICE as well. Okay. I'm not sure if I'm going to be able to read your name right. Dhruv?
Yes,
Go ahead.
that's correct. Yes, the question is that VLAM, is that like a default OptiSPICE variable name that you have to specify, or is there any other parameters that we can set?
So the VLAM, it's just a node name. So it's the connection is the name of the connection between the voltage source and the laser, and it's user defined, so you can use
Okay.
anything you want basically.
Got it.
So it's not specific for that connection.
If you allow, may I ask another question?
Yeah, go ahead.
So the other question is the optical node representation. So how does one, because currently the plots showed the units in voltage. So how does one interpret that?
Yeah. So the way that works is, Sarab, can you pull one of the optical examples, please? So the way you deal with that is through the laser itself. So the connection, so VDC, this on the left side, we have the voltage source, which sets the value for the laser, either wavelength or frequency. And if you double click on the laser VC, then you'll see that there are different ways. Right now it's set for terahertz, but you can also set it to nanometers. Then the units are going to be based on the settings of the laser. But because we're using the voltage sweep, the DC sweep as a simulation to achieve the frequency sweep, I know it sounds a bit strange, but it is a way of fitting what we do with optics into the electronic simulation environment. So then that's how you would control the units.
Okay, I think my question was probably for the Y scale, Y axis, the optical intensity, which was
Okay.
presented in voltage. So
Okay. Oh yeah, well that is because it is going through we're looking at an electrical signal.
oh,
Right.
so
That's the blue line is an electrical. The blue connections are electrical. It's going through the output of the ring resonator was being fed into the photodiode, and then the photodiode generates the current that then goes through the resistor, which generates the voltage. So we're looking at the voltage here.
right. So is there a way to probe the green wires?
Absolutely, yeah. Saurabh can definitely pull and connect a probe. We'll need to run the simulation again. There are different ways of running the simulation. The default one only exports the results for the probe. Actually, we can probably see the output of the laser, but it's just constant, so it's not going to be very interesting. Because it's constant power going into the ring resonator at every wavelength. But Sarab, can you put one visualizer on to the input of the photodiode?
I think the plot they just popped up that did show
Yeah.
the units in watts. So that does kind of answer.
Yeah.
my
And
question.
it also allows you to see multiple wavelengths. So if you have more than one laser generating different wavelengths, you can plot them in the same graph as well. Because right now there's nothing will show because we haven't run the simulation. But so the way we deal with multi-channel simulations is by keeping them in different. You can think of it as having a bus. Between, so each optical connection between two devices, it represents a bus. So we have series of optical signals going one way, and each signal going one way represents a different wavelength. And then we also have signals going the opposite way.
Nice.
Yeah. So you can run multi-channel simulations as well. For example, we have examples where you were using ring resonators as a demux, so you can send signals with 4 different wavelengths and then pick up different ones from each ring resonator. Yeah, the drop port of each ring resonator. Yeah, there you go. So this is you'll look at the power
Nice.
going into the photodiode.
Thanks for answering all the questions.
Okay, anybody else? Sarah, maybe we can talk a little bit about more advanced visualizers we have.
Okay.
We have examples that you can pull for the visualizers. So if you go examples, yeah, at the bottom we have a few examples for the more advanced visualizers. Start with the electrical one. So we can look at either an electrical eye diagram would be interesting.
Eye diagram, yeah.
Then we can show the optical and the electrical spectrum analyzer.
Right.
This is a very basic example where we're generating an electrical signal. Can you run this simulation?
Yeah.
So we can look at the results. Yeah, we're running a transient simulation and a sweep at the same time here. Okay. So we're generating different bits. And I can't quite remember. We should be able to close it.
Yeah.
Can we look at what we're sweeping here now? Because I cannot remember. Okay, let's see. Parameters.
Filter bandwidth.
Okay. All right. Yeah. So we're sweeping the filter bandwidth. All right.
Yeah.
Okay. So we're generating.
One.
Yeah, you can plot the signals. Version 1, 2, 3.
Yeah.
Yeah. Then maybe if you open the eye diagram now. So the eye diagram allows you to do many different things. It will look at, if you look at the simulation parameters, it's going to show you, so it shows you the filter bandwidth because we have swept that. And then it's going to auto calculate a lot of values for you. The max, the Q factor, bit error rate, eye height, amplitude, eye closure, opening, extinction ratio, decision instant. And you can see all these values at different sweeps as well. So the first, second, and the third sweep are all shown here, and you can also plot them together too. So on the left side, for example, you can select. Maybe we can look at if you enable a few of those, you'll see that they'll be plotted on top of each other. Yeah. The eye is usually see maybe
that's
you
the
can,
Q factor.
Yeah, this is the Q factor. The BER. So as I believe what happens here is the bandwidth is getting larger. So more of the signal is going through. Yeah. So the eye is going to be open for each. Maybe just disable all and put 3 eyes for each. It's going to be easier to see what's going on. So the signal 700, signal 7. And then there's 001 signal 7. No, that's the BER.
Sorry.
Yeah. Yeah, there we go. So let's go. In the meantime, please feel free to interrupt for questions. Now let's go look at the spectrum analyzer. So this is we're done with this one.
Yeah.
We're gonna have to run this as well. So this we're using the multiplier here. It's an electrical simulation as well. What the multiplier does is it takes 2 inputs and then multiplies them together. And you see we have 2 sine waves being multiplied. So you're going to see some multiple peaks when you look at the output. think we're, again, this one was a sweep, if I remember correctly. Yeah, so
Yes.
let's see, if you look at the second one, you're gonna see the, can you zoom at the top? I think if you do, there's a shortcut if you do control, or right click or left click and try to zoom. Should be able to go up as well. There you go. Yeah. So you see multiple peaks due to the multiplication of frequencies here. So now let's go look at the optical one as well, because it's also very interesting to see we're going to be doing, for the optical one, we're going to be doing a transient another transient simulation at multiple wavelengths, and we're going to see how it looks at the spectrum analyzer. Yeah, so we have two signals that are being, so these are at two different wavelengths that are being generated and put through a joiner. We added some noise and a filter to make it look more realistic. Can you hit run? And okay, now let's look at, you can open the electrical spectrum analyzer first. This is just an individual electrical signal.
Yeah.
At a certain bandwidth. Can close this one. And when we look at the, yeah. We see now we see the shift. See you can see the terahertz scale, and we can see the shift between the two signals because they're at different wavelengths. So we can look at them there. Like I said, we're simulating them as two separate signals, but in some cases they will interfere. Specifically, for example, if they're both hitting a photodiode, you will see the proper interference patterns at the output of the photodiode. So you'll see beating effects at the photodiode. Okay, so you guys, let's see if anybody has any questions. Okay. Maybe finally, I would like to talk a little bit about one of the main strengths of OptiSPICE, doing the electro-optic feedback loops. Sarab, can you open the example we were just looking at right before the presentation began? The electro-optic feedback, the one with the electro-optic feedback loop. Yeah, should be there, coherent detection. Yeah. So this is definitely a great example on how SPICE can deal with an electro-optic feedback loop. Now we have, on the left side, we have a signal generator that's just generating a BPSK signal, but it could be a QPSK signal as well. For simplicity, we're just going to look at the BPSK. The other thing we haven't talked much about before going into the details of this example is for OptiSPICE, we don't simulate the full carrier. We simulate the envelope of the carrier, but we keep the information of the wavelength in order to make sure that the optical devices behave accordingly. But we are avoiding simulating the optical signal at the terahertz range, specifically because it would force the SPICE engine to take very small time steps to resolve the optical signals. So the signals you have been looking at are envelopes, and we also carry the phase information, so we can handle the correct interference effects for optical signals. All right, so let's look at this example a bit. So we have the signal generation on the left side, which is which doesn't have any background. It has its own carrier, and then under the coherent demodulation, you're going to see a 90-degree hybrid and a local oscillator. So this circuit is used for demodulating a coherent signal, and the 90-degree hybrid is followed by two balanced photodetectors, which allows the circuit to split the real and imaginary part. So this is a you know a general coherent demodulator. So it's not just for BPSK. What we have done after the demodulator, so normally you would take your I and the Q signal, and then you can do you can do whatever you want with it afterwards. But here what we have done is we used a detector circuit and a controller circuit, and in order to control the frequency of the local oscillator, because if the local oscillator and the incoming signal, the frequency of the incoming signal is not locked, is not the same, you're going to have the I and the Q signals, they're going to start rotating, which then makes the ADC, analog to digital, almost impossible. You're either going to have to do the correction using an analog circuit like we're doing here, or you're going to have to process them using a digital signal processor. So we calculate, by multiplying the I and the Q, we calculate a phase difference. And then afterwards, the phase difference is sent to the a PI controller, it's a proportional integral controller, which generates which uses the error signal and generates a signal to control the frequency of the local oscillator. On the right side here, we have an idea of what the wavelength is supposed to be. So you'll see the 1550 DC offset on the right side using the voltage source, and then whatever is the difference between the 1550 and the incoming signal, or between those two signals, then we use the summation to correct the frequency of the local oscillator. Actually, let's see what the name we have used here, because we had a question earlier about the name. If you right click on the name of the signal, I think it's VLAM2 probably. Click on the connection. Yeah. Name. Yeah, you can look at the signal names and the users. Oh, it's just called signal 3. We might want to change that. Can you call that VLAM? I think maybe at one point call that VLAM2. Let's double check to make sure. Okay, yeah. Okay. Can you go back to the local oscillator now? Let's see what the connection is. That's the signal generator on the right side. The laser on the inside the blue box. Yeah. Yeah, double click on that. And let's look at the optional. Yeah, VLAM2. So these are connected now. So let's first disable the connection. So just disable the VLAM parameter and run the simulation once. Yeah. And let's look at what's going to happen to the I and the Q components of the incoming signal. All right. Can you launch the waveform viewer? So VI and VQ are the real and imaginary parts of the signal we're interested in. And you can see that you have them multiplied by a sine or a cosine term. And VLAM2 is oscillating as well because the error signal is changing. So what we have done here, actually, we have forcefully made the carrier frequency of the incoming signal move over time as the carrier signal of the carrier frequency of the incoming signal changes. You'll see rotation in the I and the Q, or the sine and cosine terms. Now close this and let's enable the I and the feedback within the laser. Now let's run it again. All right, can launch the waveform viewer, please. Yeah, now we can clearly see the signals. Obviously, because this is a BP, can you drag and drop the signals together on the same plot? Obviously, the PID is not perfect, but eventually it makes sure that the signals are locked. So we can clearly see the difference between the BPSK signal, the I and the Q channel. The Q is supposed to be mostly 0, but because there's a slight shift in the phase, the carrier frequencies are locked, but by the time you lock the frequencies, there could also be a difference in phase. So that's what we're seeing. There's a bit of a leftover phase difference, but the frequencies are for sure locked. So we don't see the rotation anymore. Yeah, you can put the VLAMs on top of each other as well. Yeah, now you can see that there's a bit of delay in the control signal, which leaves a bit of a phase difference. But other than that, we can see the signal locking. Okay, so maybe if you guys don't have any more questions before we conclude, I would like to say a few words about the differences between the standalone version and the plugin version of OptiSPICE. So here we have looked at the standalone version, which comes with a fully featured engine, its own user interface, a schematic editor, the waveform viewer, and additional parameter extraction tools that we haven't talked much about today. And the plugin was developed after the standalone version. And the idea is to get close and support the photonic integrated circuit design directly within the simulation environment or design environment that people are very used to using, like Tanner. So this is, and we're working on other integrations as well right now, but the one that we have already launched is working with Tanner, which was developed originally by Mentor Graphics. Now it's Siemens. The way it works is they had Tanner and other EDA vendors had their own simulation tools. So they had their own SPICE tools, and we developed an optical device plugin to be used with other simulation engines. So the plugin works together with Tanner OptiSPICE, for example. So when you use the plugin, you have to have Tanner's Edit or Tanner's Schematic Editor to be able to, and obviously Tanner's simulation engine. So you would use the same user interface that you're used to. If you already know how to use Tanner, you can use our plugin very easily. We have developed libraries of compact models to be used at the same time on the same engine as OptiSPICE. So functionally, it would produce the same results like the standalone version, but it is a much it is very useful when you're designing a photonic integrated circuit. For example, let's say you have a mask layout and you would like to extract the netlist from that mask layout and run a simulation. So the plugin allows you to do that. Our OptiSPICE plugin allows you to run the simulations after you have extracted them. We're also working with various fabs to develop PDKs. So how that works is that we take their optical device measurements and specifications, and we make sure that we map them onto the devices that OptiSPICE knows and recognizes. So when you work with a fab, for example, we have one with HHI. When you work with a fab, you can get access to Tanner and the PDK. HHI is a PDK for Tanner, and we have optical device library for their PDK. So what you can do is, as soon as you do your simulation for your photonic integrated circuit, you already know that your devices have been validated. We'll be talking more about this and the design flow and the workflow of Tanner and OptiSPICE in our next presentation. I would like to thank everyone for listening. If you guys don't have any questions, I think we're good.
Thank you so much, Cem and Sorab. Any questions? Okay. I think we have a question from Amin. Go
Yes,
ahead,
hi.
please. Hi.
Can you hear me?
Yes.
Yeah, thank you for your presentation. Sorry, is there any possibility to have the recorded version of this presentation?
I think the recording will be available. It will be sent to all participants. I will check with the IT team at CMC.
Thank you.
Yeah, but it should be available. Yeah.
Thanks.
You're welcome.
Another thing I want to mention is we'll be making trial versions of our software available to people who would like to use it.
That's good. Thanks, Cem. Yeah, it's good to try the software. Yeah, after this demo. Yeah. Thank you so much, OptiWave, for that. So to request your trial, just contact us or reach out to OptiWave directly.
Go ahead.
Yeah.
So I have a question. Is there a way one can call the OptiSPICE from a Python or a MATLAB and run the simulation and then have and get the output back into the Python or a MATLAB for further processing?
Absolutely, that's a very, very good question. So the way OptiSPICE standalone works is we have a user interface and we have the simulation engine, which are independent of each other. So once you generate a netlist, all you need to do is to call the executable and pass the name of the netlist through a terminal, and you can do that with Python or any scripting language. So as long as you can generate, and the netlist doesn't have to be, it's a text file. It doesn't have to be generated from the user interface. It can be generated via a Python script. So that's how you can generate the netlist from your Python script, call the simulator, run the simulation, and then to load the results back, we have two possibilities. One is we generate the data in two different formats. One is a text format, and the column information is stored in an XML file. So you can use these two combined to load the data, or the newer version, OptiSPICE 6, also we have introduced HDF5 files. So the simulation results are automatically exported as HDF5 files. So you can load these HDF5 files onto Python and look at the data. And in fact, I believe this is what our MATLAB example is using. So you don't necessarily need to link the MATLAB from the user interface. You could just use MATLAB to generate whatever netlist you want to generate, call OptiSPICE, run your simulation, and then load your results back into MATLAB and continue your processing. In fact, we have done this kind of examples before for running Monte Carlo analysis.
Okay. Do you see any more questions? Jim?
No, I think we're good. Sorry, one last question.
Go ahead.
So other last question is there parallelism for running simulations or something to speed it up, or how does it?
Yeah, well, the simulation engine runs multi-threaded. So the more cores you have, the more it's going to use. You can also have controls over how many cores it uses.
Okay. Okay, cool.
Okay. So Chem, if there's no more questions, then I guess we can end the session. Thank you very much, everyone, for attending this webinar. You can contact me directly on my email if you have any questions or if you have any feedback. And also don't forget, tomorrow is another session from OptiWave about the OptiSPICE plugin and the cool integration of the optical models into TAN or EDA. So that should be exciting, I think, for people. Yeah, thank you, everyone, and see you tomorrow.